Hello everyone, my name is Saad and this is my first video on my YouTube channel. So please like, share and subscribe. And if you have any queries, doubts or any suggestions, please write a comment. I'll read and try to improve. And if you have any uh, suggestions on making an in-depth video of any particular topic, I'll try to make it. Please comment it down. I'll try to make it in the future. So today's problem of the day in the GFG is a predecessor and successor. You have given a root node, a BST and a integer key. You need to find the in-order successor and predecessor of the given key. If either predecessor or successor is not found, then set it to null. In an in-order traversal, the number just smaller than the target is the predecessor, okay? And the number just greater than the target is successor. I'll explain this when we come to and if we check the complexities, this is big of log n, and here as you can see it is big O of 1 and big O and not big O of n, because big O of n we can do simply by DFS of any traversal. In order we use in this problem, because I'll explain you why we use in order. So if you use DFS in order, we'll get auxiliary stack space as big O of n. So this big O of 1 should point towards Morris traversal, because Morris traversal is the only traversal which traverses the particular tree in an order of big O of 1 auxiliary space. So if we take the test cases, first we'll write the in order traversal. So in order traversal of a BST is a sorted order. So 1, 3, 4, 8, 9, 10. So target is 8, target is 8. So this will be our predecessor and this will be our successor as per the requirements. So number which is just smaller than the target and number which is just greater than the target. This is much greater than 8 and this is much smaller than 8. So we have to find number just smaller and number just greater than the target value. So 1, 3, 4, 8, 9, 10. So this is our target. So 4 and 9 is our required results. So if we take the second test case, so in order traversal for the same will be 1, 2, 3, 4, 5, 6, 10 and 11. So target is 11. So predecessor is 10, which is just smaller than 11, and number just greater than 7 is nothing. So we'll take as -1 or null as stated in the question. So target is indeed 10 and 11. So for the last test case, 1, 2, 3 is the in order, 3 is the target, 2 will be the predecessor and -1 or null will be our successor. So before we understand the how we'll use Morris traversal, before that we'll try to understand what is Morris traversal for in the first place. So Morris traversal states that if you are at current node CURR current node, we'll check if there exists a current dot left, and in this case it does. So we'll go to the rightmost node, which is 6 here, and we'll just point the right of this node. 6th right will now point to here. Before that it was pointing to null. Here you can see that it was pointed to null. This root dot right is null now, but in this particular algorithm you have to point it to current where we are standing, and then we have to move left. So I'll move the current pointer to left. Current is here now. So again we'll do the same thing. One current dot left exists, we'll go to the rightmost node. Here the rightmost node is 1 itself, so it will the root the right pointer will point to 3, and then we'll move to the left. Here is current now, so left doesn't exist. So in the Morris reversal will directly print the value first because left doesn't exist, so we are at root node itself, so we'll print that value, which is 1. I'm explaining the Morris reversal now, not the algorithm required for this particular question. I'll explain the Morris reversal first and then explain, because it's just a 2-3 line change from the original code. So left is null, so we'll move print the current root node value, which is 1, and then we'll go right. Current will go to right, and current right will again go to 2. So we are again at 2. So again we'll do the same recursive thing, and we'll check if left exists, and if left exists here, we'll check if right is null, or if right points to itself. Means if right points to null, here this is right, not left for the explanation sake, and this, if the pointer is null, we'll just attach a pointer. If the right of this node is not null and it's pointing to the current node, we'll remove this, we'll print the value of current node, which is 2, and then we'll go to right. Yeah, we are here. We'll do the same thing. We'll go to we'll see if left exists. Here it exists, so we'll go to the rightmost node and we'll point to this particular node, and we'll go to the next, which is current dot left, which is 3. So we'll check if 3 left exists for the current node. If it doesn't exist, we'll just print, first we'll print the value, then we'll go to the right node. So again we'll check left, and here left also not exists, doesn't exist, so we'll print the value 4, and we'll go to the right of the current. So here we'll reach again, because it's pointing to the this, it's pointing to this node. Again we'll do the same recursive thing. Left, we'll check left exists, so we'll go to the rightmost node, which is 4. If you will check if it's pointing to null, or if it's pointing to the current value. So here it's pointing to the correct current value, which means we have traversed all the nodes from the left side of the subtree. So we'll remove this particular connection, we'll add this in the in order list, and we'll move the current pointer to current dot right. So current dot right is here. Again we'll check left. Left doesn't exist, so we'll add the pointer 6, value 6, and then we'll go to the right of the particular node. We'll reach the root node again we'll do the same thing. Left, we'll check if it exists. It exists here, and we'll go to the rightmost node, which is 6, and we'll check if it's null or it's pointing to current node. So here in this particular case, it's pointing to the current node itself. So 6 is pointing to 10, so we'll remove this particular pointer, and we'll note down the value of the current node, and we'll go to the right of it. So here we'll check for left. Left doesn't exist, so we'll take down the node value, and we'll go to right. So here current dot current dot right is equal to null. So we reach null. So whenever we reach null, there we stop the while loop. So we'll use while loop instead of uh, recursive approach, because recursive approach requires big O of n, which DFS uses. So we don't use DFS in this particular question as per requirements. So if we do the same thing, and for this particular problem statement, the thing that we have to check is left side of the, so as I have explained, the left side of the subtree will contain all the values smaller than 2. For the same case, this complete subtree will contain value less than 10. And in the Morris traversal, whenever we reach complete the left side of the tree and we come back to the current node, we'll check two conditions. We'll check every root node will check two conditions. If root dot value is less than the target, from here we'll get the predecessor. Then we'll make two variables, predecessor as null first initializing and successor also as null. So if root dot value, because we have checked all the left part of the tree, we'll come to this root and we'll check if it's less than target. Yes, it is. So we have to make predecessor as root. So because we have to return node values, not the value of the node. And I, also we have to check if root dot value is greater than target, not equal to, because we don't want 11, we want the predecessor which is next in the in order list. We'll do successor as root. This will do whenever we are printing the data. So as I've explained, we'll print the data. Instead of printing the data, we'll do this logic. So we'll go to GFG and code this up. So we have to return array list of nodes. So we'll declare array list, name it as usual, array list. We'll make two variables, p which is predecessor will be null first, and node successor which will also be null for the initialization, while this is the, you can say, the direct code for Morris traversal. If you don't know, I'll highly recommend watch a video or some blog which explains the code as well as the implementation as well as the theory of Morris traversal before attempting this question. So if root dot left is equal to null, so we'll print the data. I'm just writing the Morse code, then I'll replace this print data with the logic. First I'll complete the code of Morse traversal, then we'll go to root dot right. Because left is null, we have to go to the right. Else we'll make another current node equal to root dot left, because root dot left exists. So while current dot right not equal to null and current dot right not equal to root. This is very important because if we don't write this condition, we'll get a while true loop and we'll get a TLE. So this case comes when you have already marked this and again you have come here and we'll check again and we'll try to assign here, but we'll check that, we'll see that it's already assigned. So we'll remove this and we'll go to the right and we'll do the same. So current is equal to current not right. So we have two possibilities, current dot right equal to null or current dot right is equal to root. If current dot right is equal to null, then if current dot right is equal to null, we'll just assign current dot right is equal to root, we'll assign the value and then we'll go to the left, current is equal to current dot left. And if we have already covered the left subtree, then we have to go to the right subtree. Before going, we'll make current dot right is equal to null and we'll go to the right is equal to root dot right. Here it's root, not current, sorry, root. And here before going we'll print the data. So print the data is the logic that we have to write. So we'll write the logic. Root dot data is less than target. We will make predecessor, because predecessor is the value which is less than target. So predecessor is equal to root, else if root dot data is greater than target, which means the successor is equal to root, and then we'll break. I'll copy the same logic and paste it here. And we have got the predecessor and successor. So we have result dot and predecessor, result dot and successor, and we'll return result. We'll check. Yeah, we don't get any errors. We'll submit this. Is the same logic, just 3-4 lines I've added. If you don't know Morris traversal, please go and watch video on YouTube for Morris traversal or any other blog that you can read, which explains the complete code and the implementation of it. Before that, before this particular problem, solve that particular problem. It is also in GFG Morris traversal. If you search Morris traversal, you will get that particular question. Solve that question, then you can solve this question very easily. So thank you for watching. Please like, share and subscribe. This is my first video. I'll hopefully improve, because there is many things lagging in my explanation. I can feel that, but I'll try to improve. If you have any suggestions, please comment down. I'll read and try to improve. And if you have any suggestions on how of what videos can I make about a particular topic, I'll try to make it in the future. Thank you.